13, lesson about light. Remember, on the inside we have the study guide and the answers to that, so whenever you want to start working on your quiz preparation, you have the tools that you need. Day 113, Introduction. Purpose. You will learn how the previous concepts of sound waves relate to light waves. You will learn how light is made. Relevance. The study of light is a basic concept of physics, just like the study of energy, or the study of electricity, the study of fusion and fission. I didn't enable it. Okay, let's take a pause here from videoing and let me enable a quiz for folks. Enable until I didn't hit the start or save button. That's what's wrong. Oh. Too many buttons here to hit. There's like 6 different things that I have to hit all the time, and I never remember all 6 of them. Okay, see if it's enabled now. Is it working?
Yes, sir.
Hot diggity dog diggity. Okay, back to our little videoing lesson here. Success. You'll be able to say what light is, how it's made, and how to measure it. We have a homework assignment today and a quiz next week. Now, this is a really interesting optical illusion. Our eyes, believe it or not, are very poor witnesses. Just because somebody says, I saw such and such, does not guarantee that that truly is the case. This is especially true when it comes to criminal cases in a court of law. You kind of have to take things with a grain of salt when somebody says, I saw a yellow car. Because if it's at night and they're driving underneath bluish street lights, what might appear yellow to them at that moment is actually a different color when it comes to daylight, for instance. There's all sorts of very, very interesting experiments that people do with our brains and our perceptions. But look at this here. Okay, the ability to fool our eyes is well known. We've all seen optical illusions. Below is a picture where it looks like the squares are either a dark shade or one light shade. Right? These all look like they're either black or white on a checkerboard. Actually, it's much more complicated. Our brain recognizes that it's a checkerboard of 2 colors with a shadow running across it. The brain says, I've seen this situation very often with shadows on gray and white patterns. And so it convinces our inner self of what the brain expects to be the real case, even if it isn't. Actually, squares A and B are exactly the same shade. So let's see here. Let's cover up everything else. We're going to cover up these squares except for A and B. Right now it looks like A and B are black and white. Definitely different colors. Let's cover this up. Are you seeing it now? And I got to tear a little narrow piece. Now you can see that A and B are the exact same shade. But holy cow, you put it in this context, and I would swear that B was a lighter color than A. I could go to a court of law and I could say, yeah, they were definitely different. They're definitely the same. Pretty amazing. Okay, we need 20 minutes in order to do this, it says. We only have 10. So you know what? I don't think that we should try to rush things. So we are going to go down here, though. We're going to go as far as this spot here because it's a fun game, and it'll be about 10 minutes. And that way tomorrow we can focus on things. Let's see here. Yep. Let's start up here. Let's do this first page. The study of light is called optics. Remember that the study of sound was acoustics. Optics, like an optician, is a person who takes care of your eyeballs, who gives you reading glasses. Ophthalmologist is eye, nose, throat. Ophthalmologist, or is that just eyes? That's just eyes, ophthalmology. Okay, light is made of electric fields, and magnetic fields. They're labeled E and B. So let's see here. Where's E and B? Here's B, and up here is E. So the electric field in this case is going up and down. The magnetic field is going towards us and then away from us. These lines here are trying to symbolize arrows coming out of the paper, like my marker right now. Kind of drawing it in perspective. How do they change as they go through space? They get bigger, and then they get smaller, and then they flip, and then they repeat. So here, the electric field going up and down on the paper. It gets bigger and bigger and bigger, then smaller and smaller and smaller, then it flips, and it goes smaller, or bigger, bigger downwards, and then smaller, smaller downwards, and it's going to flip again. The magnetic field, it's going to go up and down out of the paper, like this pen, and it's going to get bigger and bigger up out of the paper, and then smaller, smaller, and then it's going to go into the paper, flip around, and it's going to get stronger and stronger down, and then weaker, weaker, and then it's going to flip again. The two components of light oscillate at 90 degrees to each other. 90-degree angles, always. The magnetic field is always perpendicular to the electric field, always. And so they're called perpendicular vectors. So we can put in that symbol for perpendicular. Remember that little square thing that we learned in geometry class? We can put those in those little nooks there, little corners. Let's put away our phones, please, if you are up front. Focus on the notes, please. Because of the two components, electric fields and magnetic fields, light is often called electromagnetic radiation. Electromagnetic radiation. Light is called this because it radiates in all directions from a source. So not all radiation is bad. We talk about radiation usually with nuclear power plants, but there's other kinds of radiation too. Anything that radiates outwards, spreads out in all directions, is radiation. In normal light, electric fields of different light beams are arranged randomly. So on one little piece of light, the electric field here would be pointed upwards, with the magnetic field coming out of the paper. With another little beam of light, you're going to have the electric field pointed, let's say, sideways like this, and the magnetic field is like this. Still at 90 degrees to each other, but a different orientation. When all their beams have electric fields orientated in the same axis, it's called polarized light. Polarized. So imagine throwing a pencil through a slit in wood. It only works if the pencil is vertical. So if the pencil is lined up with this little hole in the wood, then it can go through. With light rays, it's not quite so precise, but light will be diminished if it's not orientated as the slots. We'll play a game with that right now. We perceive light of different amplitudes as brightness, just like loudness with our sound waves. And we perceive light with different wavelengths. Is that going to be the next one? We'll talk about different wavelengths on the next page another day. But we're going to stop there and we're going to play a game with this right here. Let's see if we can play for some candy. I have here a box. I have a box with a slot in it, and we're going to try to throw this stick so that it goes through the slot in this direction. This stick represents the electric field of different lights, and you're going to have to get it through the slot.